Streaming on OBS and just verify that it's up first before I continue the discussion. Yep, it is up. Okay, very good. All right, so I'm going to read this from a bottom up fashion. Okay, so the bottom up fashion says if we define L to be S exclusive or with O, then L equals to 1 if and only if VSXM is less than VSYM. Okay, so first of all, VSXM and VSYM, we know what that means, right? The signed interpretation of the bit pattern X up to M bits, right? That's VSXM. And then VSYM is kind of the same thing, the signed interpretation of Y as a bit pattern up to M bits, okay? So now the big question is, what are those three things, right? So first of all, we have L, but L is not your concern because L is defined here. So you go like, okay, so we'll just let L to be defined to be the exclusive OR between the S and the O flag. So the next two questions that you will have is, what about the S flag? What about the O flag? What are those things? So now we have to go back up to find out how those things are defined. So I'll go ahead and talk about the sign flag first, which is the S flag. And it should be described, unless I forget to do it. It is the most significant bit. Right there. Okay. So right there, I defined it as S to be D subscript M minus 1. Do I need to explain it anymore? I can see some people looking at me with an expression of yes, please, without saying those words, but that's fine. What is D? In a binary subtraction, or not even binary, in a multi-digit subtraction, what is the role that I call D? What is it? Where is it? We just looked at it earlier.
The final subtraction.
It's the difference, right?
It's the difference, yeah.
It's the difference. It's the bottom row. Okay. So what is D subscript of M minus 1? It's,
oh, sorry.
yeah, go ahead.
It's the, what's the word again? It's the difference of the three least significant bits.
It's the most significant bit of the difference.
Gotcha.
It is the leftmost bit.
Oh, is it? Oh, okay.
Yeah, it is the leftmost bit. So the sign bit is really just the leftmost bit of the difference. That's what it is. Okay? So I know this looks really abstract because it's all symbols, right? Let's go back to the examples that we saw earlier, okay? Because that can help illustrate, these concepts. So I'm going to switch back to Zerno. Okay, Zerno is here. And I go back to Zerno on my other side. So now I'm going to go back to each and every single example and circle where the sign bit is. So with the first example, this is our sign bit. With the second example, this is our sign bit. With the third example, this is our sign bit. And with the last example, this is our sign bit. In other words, the sign bit is literally the sign bit of the difference, which otherwise is known as D subscript of M minus 1 when M is the width of the integers. Are we good so far in terms of the symbols, what S is representing? Okay, so we got all the sign bits from the previous calculations already. So we only got one more flag or one more bit that we have to figure out. So when you hear me saying a flag, it really is the same thing as a bit. Okay, it's just that in certain contexts, they're called flags because they can help direct the flow of a program. So in those contexts, it is called a flag. But a flag is really a bit that has a special application. So when you see, sometimes I would call it a bit, sometimes I would call these a flag. It really is boiling down to the same thing. All right, so now we go back to the notes because we only got one more symbol that we need to resolve, which is O. So what is uppercase O? Because we know what S is now. We just need to find out what O is. Uppercase O is what we call the overflow flag. So the overflow flag is defined right here. Now, don't worry, your lab has the redefinition of this throughout all the questions, so you really don't have to write this down. Okay, but what we do want to do during the lecture is to understand, but what does it do? Why is it called the overflow flag? Okay, so the overflow flag, so let's go ahead and compute the overflow flag for the examples that we have looked at already. Um, and then we'll take a look at the VS of X4 and the VS of Y4 for each example. And then you guys will go like, huh, that seems to make sense. Okay, so, but before we go there, let me just kind of spell out what overflow really is. Because some people look at this equation and go like, oh, it's a bunch of multiplication with an addition in between. No, that cannot be the case. The exclamation point is basically telling you, no, this is not, denoting multiplication and actual addition. This is denoting a Boolean expression. Okay, so all of these operations are Boolean. So if I were to say out loud, what this is we take the most significant bit or the sign bit of x, and it with the negation of the sign bit of y, and then and that with the negation of the sign bit of the difference, or take the negation of the most significant bit or the sign bit of x, and it with the most significant bit or the sign bit of y, and that with the sign bit of d. This entire thing is called the overflow flag. So what you see as multiplication is conjunction. What you see as addition is disjunction. Is that okay? And then someone is going to say, but what if, okay, I misunderstand this and just do the multiplication and just do the addition? Would that be erroneous? What do you guys think? Well, first of all, we are talking about bits, right? So a bit can only be a 0 or 1. So whether you multiply or you do a conjunction doesn't make a difference. It's only the addition that can be problematic. Because if both sides of the or can be 1s, then the addition will give you a 2, but the disjunction will only give you a 1. Does that make sense? So now we have to ask the question, can both sides of the disjunction be 1s? And the answer, I will give you the answer. The answer is no. Okay, only up to one side can be a 1. And as a result, if someone accidentally considers this as an addition, it is still okay. In this limited context, it's still going to be okay. All right, so looks like we're doing a bunch of stuff with the sign bits. So the sign bit of x, the sign bit of y, the sign bit of the difference. Okay, but if you look closer, okay, what is this saying? This is really saying, I want the sign bit of x to be different from the sign bits of y and d, and the difference. If that is the case, it has an overflow situation. On the other one, it's the same thing, except things are flipped, okay? So anytime the sign bit of x is different from both the sign bits of y and the sign bit of the difference, we have an overflow. That's basically the essence of this particular expression. So now we go back to the examples, okay? We go back to Zernal and go through the examples, and then we ask, okay, so what about these examples? Are we, what is the overflow? All right, so we're gonna look at the overflow first. So when we look at the overflow, let me use a color highlighting because that makes it a little bit easier to read. So the question is this bit, okay, is the 0 different from this 0 and also from this 1 at the same time? The answer is no, okay? X is not different from both y and d, okay? The most significant bit of y and d. So as a result, overflow is a 0 in this case. Overflow, whoops, wrong color. So we say overflow is a 0. It is false in this case. All right, my watch is reminding me to take roll, so let's go ahead and do that quickly, and then we'll get back to this discussion. Let's see. I just need to find a link to the class. And then we take roll today. I think I found a better way to take roll. This is a little bit more cumbersome than I really want it to be. All right, so the word is that flags. Flags. There we go. And then I'll give you guys 10 minutes to do this. So go to details. I'll give you a little more, just because it's easier to type 10 a.m. than 9:50 something. Save and publish. There we go. So go ahead and participate in the road taking activity, and then we'll go back to the discussion. All right. Does anyone need more time for road taking? Nope. We are all done. Excellent. All right. So getting back to our example here. So looks like we can compute L down, right? Where's L? L is the exclusive OR between the sign flag, which is S, and the overflow flag. So let's go ahead and do that. Okay. So we say L is the exclusive OR between the sign and the overflow flag, which in this case is the exclusive OR between 1, which is our sign flag, and 0, which is our our overflow flag, and that turns out to be a 1. So L itself is 1, but if you recall earlier, the L flag is indicating, so the L flag is a 1 if and only if VS X4 is less than VS Y4, right? In this case, I'm just going to be complete, even though it's kind of silly to do it, but we'll do it anyway. What is VS X4? The sign interpretation of X.
That'd be 0.
That'll be 0. Very good. Yep. And VS Y4 is still going to be 1 because the sign flags are all zeros anyway. So VS versus VU, they'll give you the same value. And then we say, okay, 0 is less than 1. It's also true. Cool. Wow, we went through all that trouble and came to the same conclusion. Doesn't seem like we really needed to go through all that trouble. Well, let's look at the second example, because there's a certain delay between what I write here and what you guys see, so I have to be careful about that. All right, so with the second one, we want to first figure out what is the overflow flag. In other words, we look at this 0 here, the sign of X, we look at the sign of Y, and then we look at the sign of D, and then we ask, is the sign of X different from both the sign of Y and the sign of D? No, because it is the same as the sign of D, so it's not. So that's why we can say the overflow is also going to be a 0 in this case. So we come to the conclusion, overflow is a 0. So now we try to figure out the L flag. So the L flag in this case is also the sign of the difference, exclusive OR with the overflow flag. The sign of the difference this time is a, what is the S flag in this example? You're staring at it? Go ahead. It's a 0, very good. And we just computed the overflow flag, which is another 0. 0 exclusive or with 0 is a 0. In other words, we have the L flag being a 0, which should mean VSX4 is not less than VSY4. Well, but is that really the case, right? So let's figure it out. VSX4, that's an easy one. That's just 0. But VSY4 is not as straightforward this time anymore because Y is 1, 1, 1, 1. So we still add up 1, 2, 4 because of the least significant 3 digits, right? But then when the sign flag is a 1, we go like, oh, what do we do with that 8? We do not add the 8, we subtract the 8 from the 7. So we end up with negative 1. So we end up with a negative 1 here. So now the question is 0 less than negative 1? Nope, it is false. So the L flag is correct because the L flag is a 0 in this case, and 0 is less than negative 1 is indeed false. Okay? And someone may look at this and go like, well, but Tech, I don't think we really need to go through all that trouble for the overflow flag because it would seem like the sign flag alone is already telling us what the answer is supposed to be, right? If you look at the first example, the sign flag is a 1, and the result is actually x is less than y, okay? And you look at the second example, the sign flag is a 0, and it turns out x is less than y is false. So why don't we just look at the sign flag and be done with it? Why do we need to look at the overflow flag? Yep.
I mean, maybe because there's overflow, or like the number is too big or something.
Because these two examples do not show you an actual situation of overflow. Look at the difference. If you look at this difference here, it is just 1, 1, 1, 1, which is negative 1. So is 0 minus 1 supposed to be negative 1? Yes, I hope so. So that means the result, the actual value of the difference, is represented by D as a bit pattern. Okay? You look at the second example, 0 minus negative 1, okay? Because we have 0 minus negative 1, and the result or the difference says it is supposed to be 1. Is that right? 0 minus negative 1 is, in fact, 1. So once again, the difference as a bit pattern, as a 4-bit pattern, was able to represent the value of the actual difference in a sign interpretation. So now we look at the third example. Okay, here's our third example. Just make sure that it's scrolling. There we go. And then we look at the sign flag of x, the sign flag of y, and the sign flag of the difference. So in this case, is the sign flag of x different from the sign flag of y and also the sign flag of the difference? Looks that way to me, right? Because 1 is different from 0 and 1 is different from 0. So, okay. So in this case, the overflow flag is indeed a 1. And the L flag is S exclusive or with overflow, which in this case is 0 exclusive or with 1, which is 1. So according to this, because the L flag is a 1, it's telling us that VSX4 is supposed to be less than VSY4. Okay, so we want to figure out those two. So now we look at VSX4, and then we look at VSY4 in this case. All right, let's do the easy one first, okay, which is Y. What is VSY4? Just 1, okay, very good. That's the easy one. What about VSX4? Okay, so I'm going to show you what we need to do with VSX4. VSX4. We have 0 plus 0 plus 0. What do we do with this guy? It's a sign interpretation. We know the 8, there's a present of the 8, but the question is, what do we do with the 8? We subtract it, right? So now we get negative 8. All right, so we get negative 8 here. And the question is asking, is negative 8 less than 1? I think so. And the L flag thinks so as well. So this is where we have an overflow. And then you guys will be asking, so what does it mean when we have an overflow? Look at the difference. What is the difference? Okay, I circled and it overlapped with the 1. So let me go back and add that 1 back here. Okay, there we go. So the difference is 0, 1, 1, 1. What is VSD4? It's just 7. Because we got 1 plus 2 plus 4, and there's no negative minus 8 here. So it really is just 7. Does that make sense to you? That when you have negative 8 minus 1 is positive 7. Does that make sense to you? It does not make sense. This is why we have an overflow. When the difference cannot represent the actual value of the subtraction, we have an overflow situation. But it only makes sense when we're looking at things from the signed perspective. Okay? So let's look at the last example here. We are doing really well in time, so I might have time to go back to actually explain how that works. All right, so let's look at the last example. Here's the sign of x. This is the sign of y. This is the sign of d. Is the sign of x different from both the sign of y and the sign of d? Yep, we have kind of the same situation, except the 1s and the 0s are flipped compared to the example right above it. Does that make sense? Okay, so now we go here and say overflow is a 1 in this case as well. So we look at the L flag. The L flag is the sign flag of the difference exclusive OR with the overflow flag. The sign in this case is a 1. The overflow is a 1 as well. 1 exclusive OR with 1 is a 0. So what the L flag is telling me is to say the sign interpretation of 0, 1, 1, 1 is less than the sign interpretation of 1, 1, 1, 0 is supposed to be false. That's what it's telling me. I'm not convinced. Okay, I want to look at VSX4 and look at VSY4 and actually see it with my own eyes. So that's what we'll do next, is to look at VSX4 and VSY4. So in this case, VSX4 is 1 plus 2 plus 4. It's just 7. And VSY4 is 1 plus 2, excuse me, there's no 1. It's 2 plus 4 minus 8. Okay, let me point out which bits we are talking about. There's no 1 here, but we have 2 plus 4 minus 8 because we are looking at the signed interpretation. The most significant bit indicates whether we should subtract the power of 2 corresponding to that position. So that would be what? Okay, 2 plus 4 minus 8 is? Negative 2. Very good. So now we ask the question, 7 is less than negative 2 is false. So you can see how the L flag is also indicating everything correctly. But does it make sense? Okay, does it make sense that we have an overflow here? Remember, this is representing 7. This is representing negative 2. 7 minus negative 2 is supposed to go even more positive, right? It's supposed to be 9. But when you look at the result, we have 1, 0, 0, 1, which turns out to be the representation of negative 7. But I don't even need to know how negative it goes because the sign does not make sense. The sign of the difference does not make sense. We have a positive quantity we are subtracting a negative quantity from a positive quantity, which should make it even more positive. But we end up with something that is negative. So it doesn't make sense. So when the sign of the difference does not make sense, we have an overflow. That's another way to look at the overflow flag, is when the sign of the difference does not make sense relative to the sign of x and the sign of y, then we have an overflow. So are we doing okay so far with all of this stuff? Yes?
I understand everything else, but just go through the O, like when you determined O equals 1. Just go through that again.
The O?
Yeah.
So okay, so let me repeat what O, how O is defined first. So O is defined to be x m. Okay, I'm not using m because we have we are using 4 bits. So it is x3, not y3, not d3, or not x3, y3, d3. Okay, so in this very specific example of using only 4 bits, this is how O is defined. Does that make sense? Is that okay? So now we look at the left conjunction first. The left conjunction is going to be false. How do we know? Because x3, the most significant bit of x, is a 0 already. I don't need to look at the rest of the conjunction because I got 1, 0 in the conjunction already. The whole thing has to be false. But we look at the second one, the negation of x3. All right, so since x3 is a 0, the negation is going to be a 1. We look at y3, it is a 1. We look at d3, it's also a 1. So we end up with 1 and 1 and 1. So when one side of the disjunction is a 1, the whole disjunction is a 1, and that's why overflow is a 1. But that's the same mechanism that you use to figure out the O for all of the other cases too. You basically just focus on the sign of x, the sign of y, and the sign of d, and then you just kind of plug it into this whole thing here and figure out whether overflow is a 1 or a 0. All right? So I'm going to give you guys some time to ask questions about all of this stuff here. And to think a little bit about, what I mentioned earlier. Remember I said 1101 has no inherent meaning until you have to use it for something. Remember that discussion? 1, is a pixel in full brightness, and 0, 1, I think I misspoke the other day. It is 1/3 of full brightness. It's not 2/3 of full brightness. But nonetheless, we are looking at 2 pixels on the screen. Or it can be, on a dot matrix printer, whether we have 2 dots followed by no dot and then another dot on a piece of paper. So 1101 has no inherent meaning, let alone signed versus unsigned. It's only when we use it to do something and we need a result, then we have to say, okay, what does that mean? What is the interpretation of this bit pattern? So what do you think relates today's class to that particular discussion? The subtraction mechanism is exactly the same whether we are dealing with signed versus unsigned numbers. Okay, because you look at the 4 examples. Did I change the way I carry out the binary subtraction? Nope, it's still the same boring mechanical thing that we have been doing, for 2 weeks? But in the end, how do we make a difference? How do we differentiate and go like, wait, this is supposed to be signed and this is supposed to be unsigned. What is the difference between when I need to know whether x is less than y unsigned versus whether x is less than y signed? What is the difference? Yep.
Whatever you pick, whether you want to do unsigned or signed itself.
Well, the difference is what do we look at after the subtraction? Do we look at T4 in this case, or do we look at L in this case? If you intend to look at the bit patterns as signed, you look at L as the conclusion of whether x is less than y. On the other hand, if your intention is to look at the bit pattern as unsigned, then you look at T4. That is the difference. Is that okay? Because this is really, really important later on in the semester, because the subtraction happens exactly the same way. The only difference is what do we look at after the subtraction? Do we look at T4 or do we look at L? You look at T4 if the bit patterns are supposed to be representing unsigned values. You look at L if X and Y are supposed to be representing signed values. That is the difference. Otherwise, everything is exactly the same. The subtraction is carried out exactly the same way, whether it is signed or otherwise. Are we doing okay so far? I mean, are we making the connections? All right. We still got some time, so let me go back to the slide and see what I missed. All righty. And we can maximize and look at the tab. Oh, by the way, this is a great Firefox extension. It's called vertical tab. So instead of having a tab bar on the top, you have a tab, basically have a tab on the left-hand side. It makes it easy to find which one is which one. Because otherwise, if I just look at the usual tabs, there's no way I can tell which one is which one because they all start with module 0 something. But when I go here, I can go to here and go like, oh, okay, so we have binary comparison. That's what we want. Okay, so what about the rest of this stuff here? Okay, if you look at all this stuff here, all this discussion, that's really just the rationale of getting to the conclusion that we have. The conclusion is where? The conclusion is right here. And how S is defined, it is the sign bit of the difference. And also how O is defined overflow. It is just this equation here making use of the sign of X, the sign of Y, and the sign of the difference. So that would be the bottom line. Is that okay? So when you guys are reading this, okay, and you go like, I really don't have time to read all the proof and all the steps to show why this works, okay? If you don't have time to do all that, then you just go to the conclusion. It doesn't mean that you don't have to take notes. It does not mean that you can just kind of skip and basically not understand any of this. It just means that you can skip the portion that shows why this works, the mathematical basis behind all of this conclusion. All right, and we got 10 more minutes, so I think it's time to go to the challenge. Did anyone go to the IBM Z Day yesterday?
No, but I was thinking about it.
Okay. You can still participate, by the way. It's just that they showed us how to do it. If you just look up IBM Z Student, which is a contest, it will still give you all the instructions that you need. Yep. All right. So let's go back to the sample question from the from last semester. So this is the question. Now that we have covered every single flag and binary subtraction, the question is essentially asking you to resolve all the question marks based on all the zeros and ones. So let me just kind of point out some of the more important points. This is O, okay? I choose to use a lowercase o in this case, just so that it doesn't look like a 0. And this is L, just because O is lowercase, I also choose to use L as a lowercase. In hindsight, that was a bad decision because L looks like a 1 now. I should have used the uppercase L, but the lowercase O, or say overflow, spell it out. But basically, that is given to you. So overflow is unknown, L is 1, and then we have the X, Y, Q, T, D rows. This is for subtraction. So we only know some of the bits, okay? We know this is a 1, we know this is a 1, and we know this is a 0, and you're supposed to figure out the rest. In other words, it is a alternative version of Sudoku using binary subtraction as the basic, engine of how to come up with the values. So you look at this and you go like, what are you going to do?
Well, we know that X is less than Y.
in a signed fashion?
Oh, in a signed fashion?
Yes, because we do not know the T, we don't know T3 in this case. So the overall borrow bit is unknown. So we don't really know how these two compare from an unsigned perspective. We just know the result is x is less than y from the signed perspective. So where do you start? All right, so question one, the first few questions are much harder because they give you the least number of bits, okay? But it should be resolvable. So we're gonna skip to the last one because the last one, or the later ones, will give you more known bits, so it should be easier to figure out. Oh, that doesn't look good. Nope. I think I might have fixed, just um, it's erroneous. Okay, what it is erroneous. So anyway, let's start with this one, or we can just go to the first one. All right. So the first one, how do you get started here? All right. So one clue is L is a one. So if L is a one, that means the sign and the overflow have to be different. So you have two possibilities, right? So you have to check out each possibility and rule out the one that is not possible. So how do we do that? So you basically say, we know that L is a 1, which means if O is a 0, then S has to be a 1. If O is a 1, is a 0, okay, the other way around. If O is a 0, L has to be a 1. If O is a 1, L has to be a 0. So you look at each subcase and see whether it is possible or not, given the bits that we have. All right, so let me just copy. I'll copy and paste this into. We still got a little bit of time, so I want to kind of show you what kind of reasoning you want to do to get this done. All right, so we copy that to the clipboard and paste onto a new sheet. So page new after. There we go. All right, so now we say, what if L is 1, O is 0, and sign is 1? So what about that case? So now we temporarily, assign values. So we say, let's assume this is a 0 and this is a 1, and see whether things will work out or not. So given this, now we can start to resolve other things, right? Because now we can, what would be the next bit that we can resolve? Now that we know T and we know D, we know Q. And what should Q be? In other words, I'm asking what exclusive OR with 0 would give you a 1? 1, very good. So we are using what I would call constraint type thinking to basically lock down a value of some unknown given the other ones. Okay, so now the next question is, what about x and y? Now we do have enough information to resolve what x and y should be. Because even though you might think, x and y just have to be different because q is the exclusive OR between the x and y. But that is not the case, because if we have a 0, 1 here, that is the only one that will work out with, that won't work out. Okay, why is this not working out? It is conflicting with something. So I'm going to have you guys to think about what this is conflicting with. Yes? Nope, no, it's not the borrow.
O would be 1.
Yes.
X is different than Y and then D.
Exactly. This particular configuration is conflicting with the fact that overflow is assumed to be 0. We don't know whether it's 0 or not. We're just testing it. But in this case, x, the sign of x is different from the sign of y, and the sign of x is also different from the sign of d, which means we should have an overflow of 1. But the assumption said, no, we do not have an overflow of 1. So now we say, that cannot be the case. So the only thing to make this work is to have a 1 here and a 0 over here. Okay, now everything seems to be consistent. So we say, yep, that's one way to go. So given this, we know, t is going to be a 0, because 1 minus 0, 1 minus 0, neither is going to contribute a borrow of 1. And is that enough for us to figure out, the bit 1? So let's check it out. How do we figure out, things in column 1? We know there's a borrow of 0 here, right? This is an overall borrow of 0. So that means x1 minus y1 did not end up with a borrow. Neither does q1 minus t1. Okay. We already know y1 is a 1, right? Can x1 be a 0? X1 cannot be a 0, because otherwise it would end up with a borrow of 1, and then we would end up with T2 being a 1. T2 is known to be a 0 already. So that means the only value that can go here is a 1. T1 can only be a 1, because otherwise we end up with a borrow. All right, well, that means from here on, it's just going forward, because x being 1, y being 1 means q has to be a 0. All right. Oh, but wait, just knowing q is a 0, how do we resolve t and d? Because if t is 1, d is going to be 1. If t is a 0, d is going to be a 0. But you're forgetting that t also has an impact on the next borrow bit. In other words, if t1 is a 1, then t2 would have been a 1 also. But since it's not, we rule out that possibility. So in this case, the only value for t1 to be is 0. It doesn't have a choice. 0 minus 0 is a 0. And now we end up with the same situation, because we end up with a t1 being a 0, and we have a t0 known to be a 1 already. It's exactly the same scenario that we had earlier. So we just basically reapply the same technique. We know x has to be a 1, otherwise we end up with t1 being a 1. And going forward, we know q is a 0, because that is the exclusive OR between x and y. But since we have a t1 being a 0, we also know t0 has to be a 0, because otherwise t1 would have been a 1. 0 minus 0 ends up to be a 0. So that is how we resolve all the values, all the unknowns. So that was, yes?
It's kind of nice because you can just check it at the end to see if you're right or wrong.
Yep, you can certainly check it. But are you guys seeing the process, what I use? So the first thing, the most important thing, before you even get started with this, is to know all the definitions. How is T of I defined in terms of xi, yi, in terms of qi, ti? That's one. How is Ti defined? How is Q of I defined? Q of I is x of I exclusive OR with y of I. So all of those definitions would be the first thing you need to recall. And then with the known bits, okay, this is the first one that is known, you basically go like, okay, we know the result of sign overflow with, sign exclusive OR with overflow is a 1. So that gives you two possible scenarios. There's not enough information, to resolve which scenario. So you play out the possible scenarios and say, if overflow is a 0, would it work out? Now I just got lucky, okay? If I had chosen overflow to be a 1, that would end up with a situation that would not work out. So that's a process of elimination. Okay, you basically say, this is a possibility, but what can I do to rule this out? Okay, what type of constraint is applicable to rule out a particular possibility? Because if it cannot be ruled out, then it is the answer. Are we doing okay so far with this? This is the kind of question, it may not be exactly the same, that you are going to get in exam 1, but it is about the application of what you have learned. Now, what about the reasoning that I just mentioned? Okay, we try out different possibilities and rule out certain things. Is that a part of CISP310? It's more along the line of reasoning, which I think is not specific to assembly language programming. Okay?
Reminds me a lot about physics, because like they'll give you like a word problem with a bunch of like known values and a bunch of unknown values,
Right.
and then you have to use the formulas that you do know to kind of gradually work
Mm-hmm.
to the end.
It might remind you of Sherlock Holmes as well. You have a scene, someone got killed and left behind certain types of evidence, and that's all you have. Basically the known zero here, the known one over here, and then the rest is unknown. Who was playing which role in the murder, at what time, what was the mean, and so on and so forth. And then you have to use what is given to you to figure out the rest. It really is logic. I mean, that's basically what it boils down to, is logic. Um, how many people have taken the logic class, which is a philosophy class? One. Okay. Do you find it helpful? In no, just in general. It's yeah, it is applicable, right? Yeah. So if you have not taken the philosophy class, which is I think it's what is it again? Is it critical thinking?
Yeah.
Yeah, critical thinking. If you have not taken that class and you still have that particular portion of your GE unfulfilled, I recommend at least looking into critical thinking because that class jives with computer science. Yep. Say that one more time.
A logic class in computer science.
Are you referring to CISP310? Or are you referring to 440? Because 440 is discrete structure, and that is basically a math class. But it's higher math. You basically end up applying, critical thinking and logic in CISP 440. So I don't teach critical thinking in CISP 440. Critical thinking or logical thinking, using logic, is not specific to a particular discipline. It is you can apply it in daily life. Okay, you go to a used car lot, and then the car salesman tell you something, and then using critical thinking and using logic, you go like, wait, hold on a second here, something doesn't add up. Something just doesn't add up. Let me figure out what doesn't add up. Then you try to ask questions, to the salesman to go like, okay, so since you said blah blah blah, and you also said blah blah blah, it is a natural consequence that this should happen. And then you pop open the hood and go like, but that is not the case. There's inconsistency in your logic, in the facts that you gave me. So you can apply logic and critical thinking, on a daily basis. So I cannot overemphasize, the importance of that stuff. But we are going to have to move on, and I will give you the lab for today.
I'd imagine that it'd be also really useful for debugging.
Oh yeah, I mean that really is the essence of debugging. You start with, instead of a body, you end up with a program that crashed with a certain symptom, right? It would be nice if the symptom is reproducible. Yeah. Then you can replay the sequence in different ways and see whether you can reproduce the same result. But certain bugs do not have the same. They don't have what we call a reproducible symptom, and those would be difficult to deal with. In my previous life or occupation, I had to deal with those kind of things, and it's really a lot of fun. Even when it's under pressure, it's still a lot of fun. All right, so the lab is called subtraction and compare, which is right below, it will be right below the row-taking activity. So I will give you the access code. All right, the access code is flags. It's on the whiteboard already, but I will show you again. So where is it? All right, so the access code is flags, and I am going to show the answers at noon. And I'll give you guys I'll just give you up to noon. What is 10 minutes, right? And then we have save and publish. There we go. So you should be able to get into the lab. right about now, even though my screen has not refreshed. Come on. There we go. All right, so you have your lab. So these are the stats for the lab. You can retry or reattempt a unlimited amount of time until 12 p.m. The access code is flags.
It's locked till 12.
Huh?
It's locked till 12.
Okay, operator error. Sometimes I do that.
Apparently, we have approximately a minute to take the line. 12 p.m. to 12 p.m.
There we go. It's due, not available from. Okay, so. It is awfully slow. Well, it says it's saved, so it should, if you refresh the screen, it should give you, yep, excellent. So I'm gonna turn off the streaming now. Hopefully everything is still healthy on the other side. But next time I'm gonna use your advice and just do the recording and then upload later. All right, so it looks like